Gilbert is a true champion of math education and a leader in the OpenCourseWare movement. His excellent course on linear algebra is one of the most popular in the world. The lectures are enlightening, and if you haven't seen them, I don't think that you'll be able to resist checking them out after today. On a more personal note, I'm just getting to know him myself, but I've had the pleasure of speaking and getting to know many of his students and advisees over the years, and it's enlightening and inspiring to hear about the positive impact that he's had on so many students' lives. Some of the words that are often used to describe him, I think, are kind, humble, deep, brilliant, and even superhero. So thank you, Professor Strang, for accepting our invitation. I think the students of Applied Math are humbled to have you here.
Thank you. Well, thanks for everybody. So I'm old-fashioned, as you see. I brought chalk, but I like this large chalk, but that won't do it. But I'll have to use the board here. I haven't got PowerPoint. And so let me just say a couple of words. Well, one word to say, since it's November 22nd, anybody who's 50 or more remembers this date in a sad way, but the country moves on. So I think when I was here last, I had one theorem that about banded matrices. Banded matrices with banded inverses that I was describing. So that was the talk last time. Today I don't have any theorem, but some thoughts on different topics. So I hope it's okay if I touch on several areas, hoping that one might interest one person and another might interest another. And actually, I realize that banded matrices are still in there. Well, and even banded inverses, actually. Let me show you what I mean. So this is then the first topic I'd like to speak about. And I'll make the matrices tridiagonal just to be to have concrete examples, but of course they could be more general. So what I'm going to start about first is just a topic that somebody asked me about by email, and I had an exciting weekend thinking of ideas about it, and then discovered that it had been done. So I'm reporting a topic that's understood, but well, of course there may be some other things, but I think it's not well known and deserves to be, and it's kind of nice. So this first question is, I have a matrix A0, say tridiagonal. I could even choose numbers. Well, I could even choose my favorite numbers. I don't know if you know, on my birthday, I got a whole lot of cupcakes, and the ones on the diagonal had 2s, and the ones next to the diagonal had -1s, and these had -1s, and the rest had nothing there. Actually, today's talk is to put something. What do the other cupcake? What numbers should go on the other cupcakes? Can I put the question that way? It's a little. I hadn't intended to do that. You see what happens when you don't have PowerPoint. You just say stuff. Okay. Anyway, but you can see that this is a very important question. Imagine, so I'm thinking here it's going to be symmetric and positive definite. So among the applications of those matrices are covariance matrices in statistics. Suppose you knew the variances of 4 variables, and you knew the covariances of some pairs, but you didn't know the others. And you can imagine that 4 doesn't give any sense of what this problem is. Typically, we now have hundreds of thousands of variables, and the covariances of each pair, it's just an unthinkable, impossible job. And yet, that covariance matrix comes into any estimate of the reliability, of the error, I mean, you understand, you know the importance of covariance matrices. So what principle can we use to fill it in? And of course, an early principle was fill it in with zeros. I mean, that was maybe the starting principle, but that's not sensible. And I'm sure there are multiple answers, but I want to speak about one direction, which is to maximize the entropy. Okay, whatever entropy is. You remember entropy as a sum or an integral of probability times log probability. Pi log pi. Anyway, it turns out that in this context of covariance matrices, the entropy, maximizing the entropy, also maximizes the determinant. So now we have a concrete question in very basic linear algebra. How do I choose those remaining numbers to maximize the determinant? And I could, so it has a nice answer. And so that's really what I'm just reporting on, as I say. Let me tell you before I could even put in the numbers there. But before I do that, let me say what the key idea is, the key result of if I maximize the determinant. It turns out, so I'm going to, is that legible, or would another color turn out? Let me just try, and you can tell me. I'm really apologetic to be so primitive here. Okay, so max determinant. It turns out, well, you get some numbers to go into the remaining entries, and it turns out that the inverse of that completed matrix is tridiagonal. Isn't that amazing? That you complete this with the appropriate numbers that maximize the determinant, and then now I'll change A naught to call it A, and now if I look at A inverse, if I invert that, and this is relevant because often in covariance calculations, in these big problems, it's the inverse covariance matrix you want, and it turns out to be tridiagonal. All these are truly zeros. So this isn't deep, but I think it's not known and deserves to be. And now we could see what are those numbers that fill it in. Well, actually, if you have ever thought about this question of what if we knew that its inverse would be tridiagonal, that would tell you how to fill it in. You fill it in so that all these 2 by 2 determinants are 0. It just turns out that the inverse of a tridiagonal matrix is a full matrix, and that's why we much rather work with the tridiagonal. But the full matrix has this property of like rank 1 above the diagonal, rank 1 below the diagonal. The whole matrix, of course, is not rank 1 because it's invertible. But so I guess what number would go there by this principle? I want that little 2 by 2 to be singular. Is it a half or negative a half? A half. Yeah, I think that's a half. And this would be probably a half for the same reason in this very, very special matrix where we can complete the 4 by 4 case. And then up in that corner, it would be, is it negative a quarter to get that one? Negative a quarter in the corners. Okay. So that's the completion that maximizes the determinant. We could create a formula for that maximum determinant, which of course depends only on the inputs. The inputs were A naught, and the formula is nice. Everything is nice about this. And I'll just put down the name that I see as the first major paper that I know about is Israel Goldberg, who, in my thinking, was the great linear algebraist of the 20th century. He's just an amazing person. Right.
Why should we believe there is a maximum?
Well, yeah, that's right. So I made an assumption about the given part, which I didn't mention, but it has to be. I want a positive. I want to live in this positive, definite, symmetric world. So this part should be positive, definite, symmetric. By that I mean it should be symmetric, and these 2 by 2s all have to be positive, definite. So that if you start right, you end right. Yeah. I think the existence is not as hard as a nice formula for it, and an explanation. So why should the fill-in be this special situation where you're completing with low rank? I mean, this is low rank is a big thing now, and that low rank signals over in the inverse zeros. Well, I think you can see why we should get a 0 there. Why should we get a 0 there? Because, okay, we're maximizing the determinant with maybe 3 or 6 variables. So if I maximize the determinant, I'll set its derivative to 0. Right? I'm just like an explanation of why we're getting these zeros. So the derivative. Well, I should put partial derivative of that determinant. So what is, I want it to be 0 at a maximum. And it's just really basic stuff. So what's the derivative of the determinant? Let me say the determinant of this 4 by 4 matrix with respect to that entry. So that's the entry I'm calling T, maybe. So the d by dt, what's the derivative of the determinant with respect to an entry in the matrix? Well, think of linear algebra. OpenCourseWare must have revealed the answer somewhere. So there's a formula with cofactors, right? The determinant is this number times its cofactor plus this number times its plus that number. Now we're there. That number times its cofactor and the fourth one. So it's the cofactor. The cofactor is the derivative, and we're setting it to 0. And now where does a 0 cofactor show up? In the inverse. So is that okay? This turned out to be that number has to be chosen so that the 1, 3 cofactor, so cofactor C 1, 3 maybe of the matrix is 0. And then, now what about the inverse? And then I'm finished with this specific topic. So you remember what the inverse matrix is? The inverse matrix is every entry in the inverse is a ratio of cofactor to determinant. So that numerator is 0. The cofactor is 0. So that entry is a 0 because it is the cofactor of that position, which is 0 divided by the determinant. Actually, I could have changed to, there's a beautiful function. Determinant is like, okay, but it's not the world's greatest function. The beautiful function for optimization is logarithm of determinant. Log of determinant is nice, and I could have used that too.
A couple of good ones.
Okay, thanks. All right, great. Okay. I'm going to move on to a different topic. Just hoping that some people may have occasion to use some of the pieces that went into that, and because you know matrix completion is a big subject, very active subject. How to complete a matrix when you're given some entries. So this is one direction. And so is completing an image. The whole idea of in-painting. If you have part of a painting, and if you have a painting and part of it is destroyed, how do you put back what you don't have? And so that in painting would be probably a different principle from this determinant, entropy principle. Okay, that's topic one. So I'll just move on to a second topic. Again, starting with tridiagonal matrices. Actually, I could start with that one again. You see, I never get away from this matrix. So now, well, I think the board has had. Can you imagine that's not there anymore? This is like. All right, back to that matrix. So everybody recognizes that matrix. Well, probably people recognize that matrix for different reasons, because it shows up everywhere in pure and applied math. But to me, that's a second difference matrix. It's really the matrix that shows up in a 1D just on an interval. Heat equation, for example, if I'm solving the equation, so now I'm on to topic 2. If I'm solving the equation ut equal uxx, and then I'll call that matrix A, yeah? Okay. So what do we do now in numerical methods with differential equations in time and space? Well, the most at one time one analyzed finite difference methods that were finite differences in t and x. But the move now is to simplify that and just think about the spatial, just discretize the spatial one, and then let MATLAB, OD45 or whatever code, or runner could have some form, solve the discrete. So I'm going to do that. So du dt equals that uxx would be au. So u is now a vector. You know, I'm just taking the most, what I'm going to speak about now is the most classical problem of finite differences. I'm on an interval, 0 to 1, say. I put on a mesh, equally spaced mesh. I'm given boundary values here at all times, and I want to know what the values are at those other mesh points. So I would have a 4x4 matrix, and that would be it. That would be the 4x4 matrix that you would see if maybe you have 0 boundary conditions here for all time. So a bar put in a with its ends held at 0 temperature. Okay, so the question is that matrix, that differential equation, to which, of course, the solution is u at t is e to the t a u of 0. Right. So this is the classical question, and I just wanted to learn more about e to the ta. What can we say? What can we understand about the exponential of that matrix? So again, you see what matrix I'm speaking about, just the classical tridiagonal matrix. And we know so much about that matrix. We know it's, oh, you've got technology is taking over here. Gonna say,
that's everything.
oh, but you're gonna go away. You can't leave me. Right?
Okay.
What can you do with that? Oh, all right. Thanks.
Hopefully one of these
Yeah.
works.
It does work. Okay, I'll join you.
Oh,
Thank you. That's. Is this just an ordinary napkin?
I think it's these ones here.
Special tray, right?
Special Cornell napkin.
There were some napkins too, but
Okay.
these
All
are the
right.
jar special for jar.
Oh, those are the special ones. Yeah. Okay. Thanks a lot. All right. Yeah, I know. Okay. Ah, yeah, that's better. Now we've got it really. Yeah. Okay. I think that. Yeah. I hope that one. Yeah. Hooray. You're a hero. Okay. Okay. So I'll leave the mesh there just as a reminder of what the problem is we're speaking about.
That was great.
Okay, so what do we know? As I was saying, we know a lot about that matrix. We know it's inverse. We know it's determinant. The determinant of these guys, it's a nice exercise for linear algebra class. If it's 4 by 4, the determinant is 5. It's n plus 1. And now we know the eigenvalues and eigenvectors. That's what I want to use that. That's knowledge to be put to use in understanding the exponential. So that's the question. How for a nice matrix like this, coming from a real problem, can we get more information than just stopping with writing e to the ta and leave it there? And of course, yeah. Well, so I have several things to say about this problem. One is that we can get more because we know the eigenvalues and eigenvectors of A, right? So if I know the eigenvalues and eigenvectors of a matrix, then I know the eigenvectors of the exponential of that. What are they? So if I know A x equal lambda x, say, now I want to know something about e to the ta, the exponential. So what are the eigenvectors and what are the eigenvalues for the exponential? Well, it's a function of A. So the same eigenvectors would work for all the powers of A, for the infinite series. So the eigenvectors are the same, and the eigenvalues are just e to the t lambda. So in that sense, so that is a great start to know but now the second thing is, first, really the zeroth thing is, do we know what the x's were and the lambdas? What are the eigenvectors of that matrix? It's a nice matrix, so you have a chance. I mean, it's unusual for a matrix of arbitrary size for us to know the eigenvectors. And we could ask, what are the eigenfunctions of the continuous problem, and that would be a great hint to the eigenvectors of the matrix problem. So what are those? What are the, if I have uxx equal, now I need some other letter, alpha u. So I'm looking at the continuous problem, and there's the discrete problem. That's always that same transfer of information between the two. And my boundary conditions are u equals 0 at this end, and u equals 0 at this end. So those are boundary conditions on the eigenvector, and I just want to know what it is in between. And of course, if I'm looking for functions whose second derivative is a multiple of them, I think of sines and cosines. And if I want if I wanted to start at 0, I throw away the cosines. And if I wanted to end at 0, then those sines, certain frequencies complete the sine. So the first eigenfunction is just that, just a sine. And the second eigenfunction would be like that. And the beauty is that it's true also in the discrete case. That's so a lot of, as you know, ideas carry strongly from the continuous problem to the discrete problem. But do exact expressions, math expressions, carry over from one to the other? Often they don't quite. If this was Bessel or Legendre or somebody else's equation, it wouldn't quite match. But Fourier, of course, he got in first and best forever with sines and cosines. And so these x's will be discrete signs. The x would turn out to be the sine of, can I just call that distance h, sine 2h, and so on, up to sine nx, and then sine n plus 1x would be 0. And you see what I mean by a sign vector anyway. And of course, it could have higher frequencies. So maybe I need to say the kth eigenvector is sine of kh, sine 2 kh, sine n kh. My point is here that that we know the eigenvectors and we know the eigenvalues. So that's one of the two things I wanted to say before continuing with e to the ta. That's one of the two things. The other thing is to mention a completely, a different question in which we again want to find the exponential of a matrix. So this other problem, which will connect to this problem, this other problem is more for people who work with networks, graphs and networks. I mean, the biggest issues to me, as an outsider, the biggest application area, you just see networks everywhere, right? Biologists, brain science, people doing the web, it's all networks. Steve would, I hope, confirm that networks are have become central, and actually the matrix that's truly central to so much of modern discrete math is the graph Laplace matrix, and this is the graph Laplace matrix. That's the graph Laplacian for the nicest graph you could think of, the graph of well, actually, I drew it already. Yeah, so you see, I'm not getting far in this talk. Yeah, it's just a graph of a bunch of nodes in a row. Well, strictly, you could say the graph Laplacian is singular, maybe has ones there. Let me skip that point to just to make the point that here we have a matrix. Well, actually, even before the graph Laplacian, yeah, is the incidence matrix. That's where graphs and matrices come together. The incidence matrix simply tells you which nodes are connected to which nodes. It has a 1 if there's a connection. So here, node 1 is connected to node 2. So I have there and there. Node 2 is connected to node 3, so there and there. Node 3 is connected to node 4, and I guess I stopped really at 4, didn't I? So that would be with zeros now, because there's not an edge from a node to itself. And with zeros here, because there's not an edge from way here to the other end. So that matrix is the incidence matrix for this very, very simple graph. I mean, I'm really speaking about model problems of model problems, because this is such a special matrix. But, so one question that comes up about graphs, networks, is communication. How good is a graph? What is a good design to allow good communication, or to measure communication, or flexibility, or how good is a design? Is that a good design? I think of that as a kind of tree structure, maybe. You know, like the only communication is like here we have a general G and is a major below a general, yeah, and a lieutenant and a private. Okay. So if the general wants to tell the private something, or if the president of the company wants to tell the guy in the mailroom or something, the message has to be passed down the whole tree. So in other words, I'm just commenting that that graph is not a good one for getting information through. But the question is, how do you measure? How can you compare two graphs with respect to that property of communication? Well, a measure that's frequently been used is the shortest path. How many steps does it take? And here we see the shortest path, of course, well, the largest shortest path, so a max-min problem would be, to get a message from that end to that end takes 3 steps. So the shortest, the largest, the most distant pair, maybe the diameter of the graph is the right word, would be 3. Okay. But that's a little crude, and one person in graph theory, his name is Estrada, and I think originally Cuban and now working in the UK, suggested that all paths should get into the measure. So he would count all paths as a measure of the communicability of the graph. Now, but he would weight the heavier, the longer paths. He would divide, so paths of length n, so I would take the number of paths of length n and I would divide by n factorial. But now, how do you count the number of paths of length n? The beauty is that you just take the nth power of the matrix. So here's what I'm going to do. Do you see what's coming? I'm going to take the nth power of that matrix to get the paths of length n between every pair of points. I'm going to divide by n factorial as a penalty for long paths, for large n, and I'm going to allow all n, all paths, so I'm going to sum that over all n, and of course I'm going to get e to the a. So there we see another place where e to the a shows up. E to the a is showing up in graph theory as a possible measure, one alternative measure of communicability. So it's another reason for getting some idea of what is what's e to the a like. And you see that this matrix, which I've still called A after making some changes to it, right? I had 2's on the, or maybe minus 2's on the diagonal, or were they 2's? I threw those away. But now what difference will that make to e to the a? If I change these to minus 2's, what happens to the exponential? That's just minus 2 times the identity I've changed it by. That identity commutes with everything. So I would just have a e to the minus 2t factor. So I'm multiplying between, all I'm saying is that factor would connect the exponential of this with the diagonal or without. In other words, if we solve one problem, we've solved 2. Is that all right? You see, there are 2 different problems. One is the classical diffusion, discrete diffusion, and another is this idea of communication on a graph. But now, so now I come back to that problem. Yeah. So how can we solve it? Well, look, we know the eigenvectors, we know the eigenvalues, so we know the matrix. Right? Can I write that down? And yeah, I can write down the e to the 2a. Oh, wrong one. Okay. Okay, I'm just going to write down what it's the spectral theorem, the central theorem of eigenvalues in linear algebra tells you that if you know the eigenvectors of a matrix and you know the eigenvalues of a matrix, what the matrix is, and vice versa. So e to the ta is I have to add up the contributions of each eigenvector. So k will go from 1 to n, and then I have the eigenvalue times the eigenvector xk, the kth eigenvector, times its transpose, xk transpose. This is for a symmetric matrix. So A is symmetric. That's where the spectral theorem is like central. You could say we have an answer here. That e to the ta makes this sum over all the over each eigenvector, eigenvalue pair, and you take the eigenvalue, the eigenvector transpose. That's lambda k, of course, and add them up. And we know the xk's are these sign guys. So we can substitute that and we have an expression. But unfortunately, it's an awkward expression. It's a sum over probably a large number of terms, and we're thinking of as large, and we just get an expression, but can we do anything with it? And I guess now, so this is, the only input now is to do something with it. What can we do with this expression for the exponential? And the idea is very straightforward, that this sum is close to an integral, very close to an integral, so that I can replace, I can change this to approximately, and I can change that sum to an integral. So it's like a Riemann sum, nothing fancy here at all. So it's like a Riemann sum, and if I got thetas in here properly as the arguments of these signs, that would go from 0 to pi, and I would be putting signs in here, signs in there. So I'm not going to give the details here, but just the main point of this second application. So I have 4 in mind, and I won't. Maybe I just stop there. That let me tell you one thing that's interesting about the result. This A is not only a symmetric matrix, it's a tuplets matrix, a constant diagonal matrix. The best of all worlds is to have a matrix, a convolution matrix, a filter. You could just every subject has got its time invariant, shift invariant, all the properties you could hope for. Well, shift invariant, but with boundaries. Right. Okay. Can I call it tuplets to name it after the mathematician who studied? So T for tuplets, T-O-E-P-L-I-T-Z. Okay, it's a tuplets matrix. But now if I square it, I don't have a tuplets matrix anymore. The boundaries start interfering. They spoil that beauty of the tuplets matrix. If I cube it, and if I take its exponential, it's not tuplets anymore. You know why I'm saying? I mean, tuplets is so important. Any constant coefficient here, like that constant coefficient differential equation, is shift invariant if there are no boundaries. If it goes all the way from minus infinity to infinity, then Fourier can operate perfectly. And suppose I solved the heat equation problem with some initial condition, and then suppose I shifted that initial condition by 5, just moved it along the axis. The solution would shift by 5. That's what I mean by shift invariant. Shift the input, the output shifts too. But now that would be true if I made this doubly infinite, if I got rid of all the boundaries. That's the beautiful case. It's infinite, but it's by far the most beautiful. If I have boundaries, then reflections, things are going to bounce back from the boundary, so it won't be purely tuplets anymore. And the nice, unexpected thing here was that, so I'll just state the fact here, that e to the ta, this exponential, is tuplets But I can't stop there. It would be wrong to stop there because the boundaries are interfering. Plus, another classical type of matrix called Hankel. So templates is like the world's best. Hankel is second place, definitely. But it's also natural. And what is a Hankel matrix? A Hankel matrix is a matrix where the diagonals, the anti-diagonals are constant. So a Hankel matrix, this isn't Hankel because I see 0, 1, 1, 0. Hankel matrices are constant on those anti-diagonals, and they are highly important. I mean, any matrix, any class of matrices with so much structure has got to be important. In control theory, that comes in. And then, so this is the final conclusion. And it comes out of the identity for sine A plus B. So well, I won't do that justice, so I won't even repeat it. But it's just elementary fact. When these signs come in that you're integrating, and you're multiplying sines by sines, and then you connect that to sine of A plus B and sine of A minus B. Okay. I'll stop on that one. Can we take just a pause, and I'll try to get this little space for the next. Thank you.
The whole board?
Yeah, as far as you can. Oh, that's whiter than ever. Now, you might be interested in these signs here, which I found. So Cornell is in great shape here. Save, do not wash was one sign. Please wash is the other. Right. So you can't go wrong is one way of putting it. Okay. Thank you. That's amazing. All right, and let me think about the next. Okay. Good. That's great. Well, I'll go with that. All right. So, topic 3, quite separate. Came in an email 2 weeks ago from was somebody who had noticed an interesting fact. I hope you'll think it's interesting. For 2x2 matrices, A, B, C, D. Well, let me take an example. Put numbers in. Say 1, 2, 3, 4. Just random numbers. Okay. Right. No pattern at all. Right. Okay. All right. So you notice, and I'm going to square that matrix. 1, 2, 3, 4. And I'm going to get, by familiar rules, 7, 10, is that maybe? 3 and 12, 15, and 6 and 16, 22. Okay. So, this guy noticed something about that here's my matrix, here's the matrix A, and here's the matrix A squared. And what he noticed was that this ratio of 2 to 3 was the same as that ratio of 10 to 15. Well, naturally, you can't resist trying to cube it, right? To see if this should happen. So here's A squared, can I put in A cubed? So I'll multiply this by this, so I get 7 and 30, 37. And I get 10 and 44, 54, is that? It's important to get these right, of course. 21 and 60, well, this is the one that matters. What is it, 21 and 60, 81. And then some. And is it true or not that this ratio of 2 to 3 is surviving out to A cubed? Yes, right? divide by 27 and you have 2 over 3. So, if it happened once, like that could be an accident, but twice is a theorem. There's no way that could be happening. Right. So the question is to prove it. And I could, leave that. Let me say, if you want to send me a proof by email, great. I mean, the person who noticed it had a couple of proofs, sort of by induction. That's a natural way to try. And then he said, have you ever seen this before? Well, actually, this gives me a chance. If there's anybody here who's seen this fact before, then the author of this paper would be glad and sorry to hear about it. But I certainly didn't know it. And then, of course, you can't resist. I think mathematicians cannot resist trying to generalize it, right? If that's true for 2 by 2s, what's the real idea here, and could it be true for 3 by 3s or n by n's? And then you take a matrix A, 3 by 3 matrix, and you square it, and you find it fails. So, mathematician never daunted, right? If it doesn't work, add a hypothesis, make it work. So, and the reason I'm including it today, partly because it's sort of interesting, and you think, where does it come from? I don't know any applications for it, but what I want to say is, it's true for tridiagonal matrices of any size. So that's the generalization. The extension is that for tridiagonal matrices of any size, that ratio of AJI to AIJ is the same. Well, the same for all n. Same for all n. This is independent of n. Yeah. Okay. So tridiagonal makes it okay. You take power. Of course, when you square a tridiagonal matrix, it suddenly has 5 diagonals and then 7 and so forth. So this is we don't stay tridiagonal, but the theorem is the ratios stay the same even when the matrix fills up. Actually, at the start, some of these are 0 over 0. You have to just forget those. Right. So, how to prove it? Again, it's a question for everybody here. The 2 by 2 case would already be interesting. How would you show that that's true in 2 by 2? And how would you show that it's yeah, I don't want to. So this is now n by n. So any matrix, any tridiagonal, n by n. Okay. Well, so when I thought of that extension, I suggested a sort of natural proof that that a linear algebra person might think of, but over the weekend, last weekend, came another proof from a guy at Brandeis, a combinatorics guy. And can I just show you that proof? It's fantastic. And he was proving the 2 by 2 case because that's what he had. That was what the email was originally about. But then his proof extends to n by n. Extends to n by n. Yeah. So here's a proof that those two. But I hesitate to do this because I would like you to think about what this might mean or how it could be extended or anything like that. Anyway, let me do this proof. So his point was that suppose my matrix, my tridiagonal matrix A, so I'll call it A, B, C, D, E, etc. So this is my tridiagonal matrix. Now that commutes with, so there's A. That commutes with A to the nth, let's say. So can I call those capital A's, B's? But of course they won't be tridiagonal. A, B, whatever. But these guys are what I'm going to care about. And then whatever. So those commute. So that if I multiply them in that order, or in the, maybe I can just tack this other one onto this side so that in one line I can multiply that times that, and I can multiply that times that, and they're equal, right? Matrix commutes with its nth power. And I'll just match up the 1, 1 terms. That's what he did. So, what's in the 1, 1 position? A plus B, C is the 1, 1 entry of that way. And if I do it this way, the 1, 1 entry is A plus B, B. Is that right? How about, what have I screwed up?
Capital B.
Oh, capital B, little c. That's right. Matrices are multiplied row by column. Yes. Oh, dear. Okay. Now, does that help? Well, anybody knows the first thing to do, right? Cancel AA. Yeah, that's, all undergraduates are great at that important step. Cancel the thing. Okay, now what do we know? So now, you see it? I'll divide by little c, so I'll have b over little c, and I'll divide by big C is b over big C, big B over big C. Isn't that nice? It just shows, you know, if you want a cool proof, get somebody in combinatorics. That's just excellent. Yeah. Okay. So that's topic 3. Are you game for one more? Of a different, just a comment, really. Yeah, just a comment. It goes back to graph Laplacians. Because I think those matrices, you just see them everywhere. And the world of spectral graph theory, all that is just where so much is happening. And those graph Laplacians, like the one we had up there before we erased, were for undirected graphs. The edges on, you remember so I'm leaving this and going back with, I'll just find a little space to do what I want to do here. That graph we had, which was just a line of nodes, the edges were not directed. And the result was we got that symmetric matrix, A0, that -1, 2, -1 matrix for the Laplacian. And the theory of graphs with undirected edges, undirected graphs, I'm not speaking as a pro, and there are some professionals here, there's some stars here. So I'm just, I'm a little bit out in left field, but I'll tell you where this is coming from. I read a couple of papers by, and I'll put his name up here, because it was a fantastic couple of days. Gunnar Wardena, who I haven't met, also he's at Harvard. He's in systems biology. But, and in systems biology, do you know, you see expressions like, I don't know what these mean, but you see A plus a enzyme producing a B. Have you seen anything like that? And then that B will split up. Well, it could go backwards maybe also. So that you could say is like undirected because it goes both ways. But this next one only goes one way. it can pop out that enzyme again and some other thing that I'll call C. That's a very famous reaction that I don't know enough to say anything more about it. But from the point of view of graph theory, because those reactions are different, or one way, some of them, you have to deal with directed graphs. And as far as I can see, the theory of directed graphs is way behind and needs to catch up. And just to even first, I didn't have any sense, and what I'm saying now might be all well known. But what's the graph Laplacian for directed graphs? What do we do differently for directed graphs? So that's my final mention, is just to take these important topics of graph Laplacian for undirected and directed, and say, for undirected, we've got a big theory, still growing and central. But for directed graph, I think we have a smaller. I'm sure it's a smaller theory. And so what are the starting points? So that the undirected one. So let me put these words up again. Then, so did I mention that he was? It turned out he was a topologist, a pure mathematician for his Ph.D. So maybe not a surprise that he was in Cambridge in England, and then went into business, and now he's come back to systems biology. So anyway, I would just Google him, and it's Jeremy Gunawartana. Okay, so I've never met him, and he wouldn't know me, nothing. Just to say this gave me a hint of where to go with directed graphs. Okay, and that's all. I'm just passing this on. That maybe for directed graphs, this is potentially, thanks, potentially useful thing. Okay. Let me just make a little space because I won't say much here. Okay. And for undirected, I don't need to write again the 2's and minus 1's matrix, because that was the simplest model you could possibly have. What do you get for directed graphs? What matrix takes its place? Well, things are only going one way. So actually, that undirected one, the 2's and minus 1's, can be put together by the finite element method, would put together matrices out of little element matrices. And the little element matrices in the undirected, so U for undirected, is that okay? For undirected, the little matrices are one for every edge. That matrix is the element matrix for a single edge. And then when you assemble those little 2x2s into the big matrix, you get the graph Laplacian. Can I just draw a picture to show what I mean? The little 2x2 for an edge would go there, and then the next 2x2 for the next edge would go here, and the next one would go here, and so on. And when you put in that in all these positions, you're doubling the diagonal, and you get 2's. No problem. Okay. And that has that matrix factors. It's just great, and I can't do everything here. So what goes into the directed matrix? And of course the matrix that's going to come out is an important one. So it turns out, based on this, that the matrix to put in those two columns give us both directions. So I'll put in only the one direction. So I'll just show you the matrix and stop. You get a 1, a minus 1, 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 say. and I'm not going to deal with the boundaries here. But so I think that's the right direction. This is all hazy. This is the right direction to go. And what kind of a matrix do I have here? Does Gunnar-Wharton have here? That's a Markov matrix. So instead of Laplace, I think it's Markov that shows up. It's a Markov matrix for, can I call that P? For a continuous Markov process. In other words, instead of du dt equal AU, which is what we had, or AU, which we previously had, now we're going to have du dt equal PU, where P is this Markov guy. And then now we're home, because, or at least we've got lots to do, because the theory of Markov matrices is intensely active. So I guess my hope for comment, and I don't have anything much to prove here that it's right, just the sense that, just the hope that it might be a useful comment, and so I just make it in that spirit, that I think the analog of graph Laplacians is something that you could call a graph Markovian or something, because it's about Markov rather than Laplace. Yeah. Okay. Well, that's my apologies for 4 unrelated or only slightly related topics on a board. I think I'll put up the sign. I'll remove the sign, save, and put please wash. Okay, thank you. I'm happy to talk to any questions, but maybe there's a reception or tea or something
There is a
after.
reception,
Okay, yeah. Anything I can do? Save it for over there. Is that good? Yeah.
There's one.
And it's time. There's one? No. Is it? Hi. Oh, hey.
I'm just curious if you, I mean, it's also possible that for directed graphs, maybe the analog of Laplacian is going to depend on what you want to do with the directed graph, right? There might be
Yes.
one matrix for one sort of question.
That's absolutely right. Yeah.
So
Yeah.
do you have a sense, like, is this particular matrix adapted for a particular kind of question? with
Well,
some-
this type of matrix, du dt equal pu, that type of problem, that's called the chemical master equation. I mean, that's an impressive name, and it's a big deal for that in that field. So that's my yeah, and I'm sure other fields would have other directions, but yes, but that matrix. So they solve big Markov equations, and you know, there's a lot of interesting mathematics in that. Yeah, yeah. Thanks, John. Okay, for tea, coffee, or whatever. Thanks.